Hi, and welcome to the Electronics and Programming Beginner's Guide. Today we're going to look at part 2 of my Back to Basics of Capacitors series. If you haven't seen part 1, I'm going to link it in the description down below. In the first part, we went over what actually makes a capacitor, two parallel plates, and we looked at some of the formulas that govern how the capacitor is formed. And then we also looked at some of the parameters that a capacitor has. We're going to begin by taking a look at the model of a capacitor. And this is what it looks like. The model obviously has a capacitor element, and that capacitor element most of the time is the major part of the model. Along with the capacitor, you have a resistor. This is what we talked about from part 1 of Back to Basics about capacitors, is the effective series resistance. Where does this resistance come from? It comes from the fact that the capacitor has leads on it. Something has to attach to the capacitor and then to the circuit board or whatever you're attaching to. And those leads are not the same thickness or width as the actual plates of the capacitor, so what you get is sort of a bottleneck effect. As the charge is leaving the plates, the charge has to funnel down into a much smaller cross-sectional area to then leave the capacitor, and so you get some kind of resistance. Depending on the construction, the physical construction of the capacitor, that resistance can be high or low. Then you have an inductor. The inductor here comes from, again, the fact that the capacitor has leads. Whenever you get a single strand of wire, that wire has some amount of inductance, because as current flows through that wire, a flux basically sets up around that wire and forms a magnetic field, and that magnetic field then is what effectively causes your inductance. Now, from what I said earlier, is that the capacitor element most of the time is the major part of the model, but depending on frequency, this inductor here can actually become very, very large, swamping the fact that this is a capacitor, and the capacitor starts behaving more like an inductor. But we're talking, very, very high frequencies, in the high megahertz, low gigahertz kind of area. But generally speaking, for most of the stuff that the average electronics engineer does, this inductance here can effectively be ignored. The most basic formula that governs the behavior of a capacitor when it's connected to some sort of source is Q equals CV. Q is the amount of charge, the amount of coulombs, effectively the amount of electrons that are stored in the capacitor, is dependent on the C, which is the capacitance of that capacitor, and V, which is the voltage stored in that capacitor. This is the most common way a capacitor gets examined, for lack of a better word. This is how electrical engineers view capacitors. This model consists of a voltage source, Vs, a switch, a resistor, and a capacitor. Generally speaking, this model makes at least one assumption, unless it's stated otherwise, and that is there is zero voltage stored in this capacitor at time zero, at t0, when the switch is closed. You can basically put pre-existing conditions into the model. So let's say that the capacitor stores half of the source voltage or something along those lines, but generally speaking, zero voltage when the switch is thrown at t0 and you have a voltage source. The reason this model has a resistor here instead of just having the voltage source, the switch, and the capacitor is that, as we looked at just a little bit ago, the capacitor always has some type of resistance in it. And so this resistor can be the effective series resistance of the capacitor, or it can be just a garden variety resistor, which is a bulk element of the effective series resistance and some other resistor, or it can be just any old resistor, which is so large compared to the effective series resistance of the capacitor that the ESR can effectively just be ignored, because ESR tends to be very low in the sub 1 ohm area, like 50 milliohms, 500 milliohms, that kind of. And this resistor could be, you know, a mega ohm. And so at a mega ohm, a million ohms, 50 milliohms of effective series resistance is entirely negligible. There are two ways to look at this particular model. The first way is steady state. What that means is at t0 you throw the switch, and then you let t, the time, run out to infinity. When t equals infinity, effectively, you are considered to be at steady state. At steady state, the capacitor here will have across it exactly the same voltage as the source, and the current through the circuit will effectively drop to zero. The transient analysis, on the other hand, is everything that happens from the time the switch is closed to before you reach steady state, meaning that the voltage across the capacitor has reached the source voltage. And this analysis, it becomes more tricky. You can actually derive the formulas that govern this from this equation here, but derivations are boring and use lots of math, blah, blah, blah. And so what we're going to look at is kind of a behavioral analysis, and then I'll just give you the equations that govern this, and we can take a look at how those work. So as we said before, the precondition is that there's no charge stored in the capacitor, and so by this formula, there's no voltage across this capacitor, so it's 0 volts. And that's at t0 when you throw the switch. When you throw the switch, very initially, what you get is 0 volts here. A current flow starts to flow from the source, because it's 0 volts here, this way through the switch and then through the resistor. And initially, because the capacitor is not charged, the current flow here is basically just dictated by the resistance and the source voltage. Just basic Ohm's law kind of stuff. As this current sets up, a voltage develops on the resistor, a voltage drop, here like that positive here, negative here. As the current begins to flow, charge starts to build up on the capacitor, and as this Q begins to increase, a voltage forms on the capacitor, and the voltage is in the form of plus minus here. When the voltage begins to form, this is when things start to get tricky, because as the voltage forms here, this voltage starts to subtract away from the voltage of the source across the resistor. So initially we had directly the source voltage across the resistance, and the current was dictated by Ohm's law. But now we start to get into the Kirchhoff's rules, that the sum of the voltages around one loop of a circuit always has to equal 0. And so the voltage across the resistor plus the voltage across the capacitor has to equal the source voltage. But because we're starting to subtract away from the voltage that's across the resistor because of the voltage that's stored in the capacitor, the current starts to decrease. And you get this sort of roundabout action that happens, that as more charge deposits in the capacitor, the current will continuously decrease. And what you end up getting, if you were to derive this, is effectively a differential equation. That the effects of the resistor and the capacitor with the source are not linear. The formula for charging the capacitor, so as you throw the switch through the resistor, is the voltage of the capacitor, Vc, equals the voltage of the source, Vs, times 1 minus e to the minus t divided by Rc. Let's analyze this formula and kind of tease out of it what that actually means. The important part of this formula is RC up here. RC is referred to as the time constant. The reason it's referred to as the time constant is that the result of R times C, you can use that to directly analyze what is going to happen. RC, the time constant, in this graph breaks out to these here. These are time constants. So zero is when the switch closes, and then 1 time constant, 2 time constants, 3 time constants, 4, 5, and 6. So time is on the x-axis. On the y-axis here, we have the voltage of the source. And so the question is, how long does it take for the capacitor, which is this line here, VC, to reach effectively the voltage of the source? And the simple answer here is that it takes about 5 time constants. Now, I understand that when you first look at this formula looks super confusing. But let's break it down into its smaller components. So E here is a constant. You might have seen it from compound interest. It's about 2.7. It's got more decimal places, but let's just say about 2.7. And that's taken to the exponent of minus t over RC. So at time equals to 0, t here is 0, and anything taken to the 0th power is 1. And so at t equals to 0, you get 1 minus e to the 0, which is 1. So 1 minus 1, this calculates down to 0, and so you get the voltage of the capacitor equals to the source voltage times 0, which is nothing, and that's exactly where we start from. When we reach our first time constant, which is RC, the first time constant gets put in here, and so you get RC over RC, which would give you 1. Anything taken to the 1 power is itself, but don't forget we have a negative here. And so what you get is itself over 1. So this turns into 1 over E. E is about 2.7, and if you do the math on that, it comes out to about 0.37 with some trailing decimal places. So what you get is 1 minus 0.37, which is about 0.63, and so at the time constant of 1, the voltage is about 63% of the voltage of the source. And basically this trend continues. As the time constants increase, you effectively get here 2 times RC. And so 2 times RC, the RC's cancel, you get e to the minus square. And so you get 1 over e squared and whatnot. And e here effectively over time decays to 0. As e decays to 0, you get 1 minus 0, which is just 1, and then 1 times your source voltage gives you the voltage of your capacitor. And so as E decays, the capacitor charges up to the full source voltage. At 5 time constants, the voltage in the capacitor is 99.3% of the voltage of the source, and so at 5 time constants it's roughly considered for the capacitor to be charged. After 5 time constants, the voltage gets closer and closer, but you're so close at the 5 time constants that it's just considered a wash and you are fully charged. So anything time-wise higher than 5 time constants is now considered to be a steady state. Now the other formula we can look at is the current through a capacitor, which is the current is IC. IC equals to Vs over R, which is your basic Ohm's law type formula for the current through a resistor times e to the minus t over RC. And again, this is governed by that RC time constant. Now, as you can see, the graph of this formula is again an exponential, just like the other one, but this is a decaying exponential versus a building type exponential. And again, we can do the same kind of analysis to the formula of the current as we did with the formula of the voltage. When t equals to 0, E equals to 1, because anything to the 0th power is a 1, and so at t equals to 0, the current is the greatest it can possibly be, and that is effectively ignoring the capacitor. And so you get this, what is often referred to as an inrush of current. Here you get the highest, and that current then begins to decay. At one time constant, that current is about 37% of what you started with, and as the time constants slowly increase, that current will decay, where at 5 time constants, that current drops to about 0.7% of the initial current. And again, that at that point the current is so low it's effectively considered 0, and this is when the capacitor is now fully charged. The other, for completeness, the other model that we need to look at is the model for discharging the capacitor, going the opposite direction, where you start from when the capacitor is fully charged, and you discharge it until it hits 0 volts. And so the model looks almost exactly the same, with 2 major differences. The first being that your source voltage is gone, or effectively set to 0 volts, which makes it disappear. And now there is a voltage stored across the capacitor, which we're going to call the initial voltage, or a voltage I. And then at T0, the switch gets thrown, just like in the other model. And if you didn't initially recognize this formula almost right away, this formula resembles the formula for charging the capacitor, but for the current. And again, you start with your initial voltage, VI, and then at t equals to 0, this becomes a 1. And as that becomes the 1, at t equals to 0, the initial voltage equals your capacitor voltage. Then as t begins to increase by your time constants, 1, 2, 3, 4, 5, the voltage decays. And so very similar to the current of a charging capacitor, the voltage of a discharging capacitor is an exponential decay. Without the little swish at the end there. It looks just like that. And if you can guess, the current of a discharging capacitor also looks very similar, with the exception of it's now considered negative. Let's go ahead and draw that up. And so the formula for the discharging capacitor, IC equals negative VI over R, so the initial voltage of the capacitor over the resistance, e to the minus t over RC. The reason why it's negative is because in our model, the initial current was going this way into the capacitor, which would be positive. But now, since the current is leaving the capacitor, the current is negative, and so, oops, forgot the negative here. And so our 0 x scale is now up here instead of down here, and the current starts at the highest current right here, and then decays this way. So that about wraps up part 2 of the Back to Basic of capacitors. We took a look at what the model of the capacitor looks like, and we looked at the formula for how much charge is stored in the capacitor. And we took a look at the 4 different formulas for how, the voltage and the current of how the capacitor charges and discharges. And I don't know if I necessarily emphasize this enough. The one thing I would take away from any of this is that the initial inrush or outrush, if you want to call it that, current of a capacitor is the source voltage multiplied by, source voltage divided by the resistance that is in line with the capacitor, and that resistance can actually be just the ESR of the capacitor, and that's usually what we refer to as the inrush current. So if you, for example, have a circuit with a bunch of capacitors in it, either for decoupling or bulk capacitor purposes, you can effectively do the calculation of how much initial inrush current you would have when you connect that circuit to a power source. If you like these videos and would like to see more, don't forget to subscribe down below, and thank you for watching.